everyone, this is Gabby, and I will be doing the first part of the analysis for the article that was titled Language Prediction Mechanisms in Human Auditory Cortex. And then once I'm done, I will pass it off to Angela. So first off, we will discuss the theoretical framework. What we are aware of is that the auditory cortex does use prediction when it comes to listening and producing speech. So let's think about what we know about prediction. Well, we know that the brain uses the top-down predictive modulation and also the bottom-up sensory input. Now it comes down to, can these two situations or methods work together, and where anatomically does this happen? So this leads us to the research question and the hypothesis. Now, these hypotheses and research questions were very wordy, and there are many. So I was able to combine and kind of bring it down into one sentence, which is presented as: if we know that the brain has natural rhythms and they sync up with the rhythms of the outside world, then we can assume that this neural activity results in temporal prediction. And temporal prediction is also described as anticipating what sound, word, or syllable will come next using the synchronized rhythms from the neural activity that was just explained. So this test or this research is to try to figure out where in the brain do these work together, and what else is the brain doing other than just connecting and syncing rhythms. Is it actually using these rhythms to predict the next sound, word, syllable? They did this with 36 or 37 patients. It is unclear, as the direct quote shows that it says 37 but only adds up to 36. But all of the patients that were participating already had the intracranial electrodes from previous epilepsy testing, so these electrodes were already surgically placed. So that just allowed the scientists to be one step ahead. Now, there were two different experiments or paradigms. The first one was kind of tracking a noise assumption or prediction, with white noise being stimulated over speakers, and the person was to click a key button every time they felt like they heard the signal, and they tracked the neural activity from the electrodes to make sure if they actually were predicting the sound or if they were just guessing or what was going on. Now, there was also a more linguistic part of the experiment where they were to answer different naming tasks and be engaged with these different cues. And then once again, all of these experiments were tracked by the neural activity through the electrodes that were located on the auditory cortex. Now I'll pass it off to Angela.
Hi everyone. So when we look at the results of the study, we find that there are two main predictive mechanisms in the brain which help us predict sounds. These regions are in the Heschl's gyrus, which is located in both hemispheres of the auditory cortex, and then plana temporale, located only in the language-dominant hemisphere of the auditory cortex. In the first experiment dealing with non-linguistic cues, when regular and repeated white noise was given, the Heschl's gyrus used high, medium, and low-frequency brainwaves to detect different features of the sound, and in doing so, it was able to pick up different details of sound, such as its loudness or the rhythm. But even after the repeated sound stopped playing, the Heschl's gyrus continued its activity in low-frequency brainwaves, which ended up helping the brain predict what the next sound would come, like when it would come next. However, when the plana temporale was given the repeated white noise, it did not have the same steady brain response as Heschl's gyrus. Instead, it responded with a quick transient response right after a new sound began. So in this first experiment, the plana temporale didn't really show that it helped with predicting sound. Instead, it really only noticed when a new sound started. When we look at the second experiment dealing with linguistic cues, the researchers measured how the brain tracked the envelope and acoustic edges of speech. So when we look at these features, the envelope deals with the overall loudness or shape of speech, whereas the acoustic edges deal with where the loudness in speech rapidly changes, like at the start of a new word or at a new syllable. And when the researchers looked at Heschel's gyrus, they found that the brainwaves followed both the envelope and the edges of speech, just like how it did with the white noise in the first experiment. And the plantar temporal showed a small burst of activity right after a new sound or a new word started, which is also similar to how it reacted in the first experiment. Something that was also found with the plantar temporal was that the brain actively was strong when listening to sounds coming from external sources, but completely absent when the person themselves was speaking. This shows that the plantar temporal helps differentiate between sounds coming from people themselves and external sources. In this last experiment, it also showed that Heschel's gyrus was direct. It also showed that when Heschel's gyrus was directly stimulated, it made it harder for people in the experiment to understand speech. And when the plantar temporal was stimulated, it made it harder for the people in the experiment to speak. So, what do all of these findings really mean? These findings show that the auditory cortex doesn't just operate rhythmically, but does help the brain predict speech cues and other acoustic stimuli, which helps to support the author's original hypothesis. When we look at how Heschel's gyrus and the plantar temporal reacted to direct stimulation, we can see how these areas in the auditory cortex not only help with finding rhythmic patterns in acoustic stimulation, but also have an effect on speech predictability. These findings really show that the Heschel's gyrus helps most with steady listening and prediction, and the plantar temporal responds quickly to sounds and helps differentiate between our own voice and external stimulation. So when I was brainstorming on the real-world implications of these findings, this is really what I came up with. These findings can really help improve hearing technology. Now that we can see how the Heschel's gyrus and the plantar temporal work together, hearing devices could be made to help mimic the brain's way of focusing on important sound changes and predicting what comes next. This could help make speech a lot clearer for users in noisy environments. Also, understanding these findings can help us empathize with our future patients. It shows us how closely related speech and hearing really are. So, if someone had damage to either one of these two areas in the brain, they'll most likely be struggling with hearing, understanding speech, or even speaking. So, understanding how these inner workings work can really help us understand what's going on in our patients' brains.